Good afternoon, ladies and gentlemen. Today we cover a topic which is very exciting and it's very important, especially if we deal with high-dimensional data, meaning we have data matrices which have more than 100 columns, for example. How to deal with that with certain learners. For example, k-nearest neighbor classifier has quite some trouble with that high dimensions. If he has to look for all neighbors in these 100 dimensions, so it would be nice to have a representation of the data which is sparser, which is denser, which is condensed to only a few, but only relevant dimensions. And that's the topic about dimensionality reduction. And we learned today 5 technologies or 5 techniques how to do that. And one of the most important ones is PCA. It's called principal component analysis. It's based on an eigenvalue decomposition, and it's a linear technology. So it has its advantages, but it also has its drawbacks. We will see. It's quite an important one. The picture here already shows the main idea of the principal component analysis. If we have a bunch of data here, we could assign, for example, or assume here that it is drawn from a multivariate Gaussian distribution. It looks as if the data is more or less on a straight line, and the principal component analysis tries to find a representation of the data in a subspace of the features here, x1 and x2, which is lower in dimension. For example, which could be only represented by laying the new axis, let's call it y or y1 here, along this direction, c1. That's the main component, that's the first principal component. And by doing this, actually we would say all the data actually are one-dimensional, more or less. There's some variance in the other direction, but the main variation, the main variance is along this direction, along the component C1. So a good representation of these data in lower dimensions is already the projection of all data points onto this line. This is already a dimensionality reduction to 1D by this 2D. And of course, we will do it in much higher dimensions, but it's enough if you understand it for 2 dimensions, because the rest is just a knowledge. Okay, we start with the curse of dimensionality. We've seen that before. It's just an introduction and a repetition. Where does this come from? That in high dimensional space we have problem sampling data, because the data is getting really sparse in these high dimensional worlds. And then we go to something which is very helpful, the manifold hypothesis. What is a manifold? A manifold is kind of a lower dimensional space, which is more or less continuous. Doesn't need to be a hyperplane. It can be wrapped and round and so on. But it is assumed in this manifold hypothesis that the data lies on a lower dimensional structure. It doesn't use the full representation of all features vectors, because if we could, for example, define curvilinear coordinates along this subspace, we would save coordinates, we would save dimensions, and could represent the data in this manifold with lower parameters. And the question is now how to find these lower subdimensional spaces. So it's a part here of unsupervised learning. We don't have a label, a line. We just play with the x's today. We don't have a relationship to something we want to predict. It's just finding structure in data, which we've never seen before, and we want to do this automatically. Principal component analysis, we look at in depth, and then the other 4 methods, which are called manifold methods, which are based on this hypothesis. They're just good to know. We probably look deeper into TSME, here the T-distributed stochastic neighboring, because it is really powerful. It's complex to use. It's not that complex to understand, but it's really complex to use because you have some parameters One parameter is called perplexity, and I would say, yeah, it's quite perplexed to use that one. Huh? So we have to play a little bit. The curse of dimensionality says, yes, for example here, how much of the data do we need to sample in each dimension if we want to have some fraction of the volume in a high-dimensional space sampled. For example, in a one-dimensional space, to have 50% sampled, it's enough for each dimension more or less to have 0.3. So we have to sample every direction 30% of the data is enough, and then we can sample it to 50% or so. If we go to higher dimension, these curves get steeper and steeper. It's like a square around the nth root of that. And you would say, if we read this curve, for example, in a 10-dimensional data space, if we want to have covered 50% of the volume in this 10-dimensional data space, we need to sample on each axis more than or about 90% of all the data. And this is infeasible. And this grows exponentially with the dimensions of the space. So there is just a limit. At some point, we come to the edge where we cannot do it anymore. So it would be nice if we have data in these high dimensions, if we could condense these data somehow. If we could project these data into a lower dimensional subspace, where we escape these curves of dimensionality, because we can then sample in that lower dimensional space or represent our learner in that space. Yeah, one dimension is easy to sample. Here it grows like the squared and the cube and so on. You see, for 10% of the coverage here, we need 10 to the power of p, where p is the dimension of such boxes to cover actually that volume in the p-dimensional space. That's more or less the curse of dimensionality. Okay, we will play today with the MNIST dataset. You probably have already seen that dataset. It's that famous dataset of the SIG numbers, the postal number, which should be read automatically, or which are read now automatically. And each number there is actually, in our dataset, represented by an image which has 28 times 28, I think it's 784 pixels. So the dimensions of each pixel is actually 284. So to represent a number in the MNIST dataset, we need, first of all, a feature vector which has the dimensionality 284, which is quite a lot. And probably there's a way to do it in a better way, to do it in a sparse way, because the pixels are often very highly correlated. If we look at the number in this data set, we have a lot of zeros, white backgrounds, and so on. Then we have gray levels, and these gray levels are actually connected. The neighbors, if one neighbor is gray, there's a high probability that the next one is also gray or even black. We can use these correlations in the data to reduce the dimensionality of the data set. And we should do it. We should do it in any kind, because if you want to make a number classifier out of this data, and if we work on the 284 dimensions, we will not be very successful. We won't be able to train a really good classifier. So if we think of a k-nearest neighbor classifier, it has to sample and calculate all the distances in this 284 dimensional space. And this is quite a lot of work. So the dimension in this case for an image, it's the number of pixels. And if they're continuous grayscale 16-bit numbers or so, that's about the resolution we have. Okay, dimensionality reduction is therefore actually a process of reducing these dimensions, for example by pictures. And we do it here not with neural nets. Convolutional neural nets, actually they do the same thing. For the first layer, the convolution nets, where they train actually the convolution image filters, actually is nothing else than generating features from high-dimensional representations of the data to lower dimensions. It reduces the dimensions. We come to it at the end, just to give an outlook what neural nets do in case of autoencoders. But now we cover actually classical methods. So there are two things which we can do, and we have to discriminate these two. Actually, we can do feature selection, feature reduction, means we could just leave out something. Yeah? We could, in the MINS dataset, say, oh, we leave out all the pixels that have values which are smaller than, gray values smaller than 5, for example. Would not be a wise thing to do, but it would be a feature selection. Yeah? We could reduce and only concentrate on that features where we have, let's say, black or gray dots. What we do here is actually a feature transformation. We take all data and transform it, project it to the relevant subspaces. That's the topic of today, feature transformation. In order to, the two purposes why we do it, actually feature generation for good learners, because they have really meaningful features and lower dimensional features. The next thing is actually, if we have very high dimensional data, just to visualize data. How do we visualize correlation in a 284 dimensional space? The idea is to project it to 2 or 3 dimensions so we can look at it, yeah? And learn from the data, because we've never seen and we cannot really dive into as humans into these high dimensional spaces unless we project it to one meaningful subspace in 2 or 3 dimensions. The whole taxonomy of dimensionality reduction, the overview is more or less, we have actually linear methods, easier, and non-linear methods. The linear methods are mainly based on principal component analysis, and here again, I come back to the topic of kernel. The kernel trick is a nice thing to make out of a linear method kind of a non-linear method. We can map it to, it seems to be contradictory, that we actually want to make a dimensionality reduction by introducing a kernel which actually blows up the dimensions again. But it works, and actually can also cope with some deficiencies the linear PCA has. Because it's linear, it cannot unwrap very complicated hyperspaces, and this one can. Then we have other methods, and here the difference is also what we need as input is the full data matrix. And if we need that, actually, there's also an advantage. We can retransform the whole thing. We can make the inverse transform. Once we have the compressed data, we can apply a retransformation, a back transformation, an inverse transform to get the representation back in the original space. It's like an encoding, decoding. This is what we can do in these linear methods. Here for non-linear methods, we only need actually the distance matrix. And distance matrix is the matrix of all pairwise distances. And these pairwise distances in these high dimensional spaces, they represent something like the similarity between samples, between data points. The closer they are together, depending on how we define this distance, the more similar they are. So we can later cluster them. We can now bring these together to reduce the dimensionality. So we look at multi-dimensional scale. That's for MDS here. We look at the isomap here, and we look at the T-stochastic neighborhood. And I just listed other ones. Probably this one you've already heard, the self-organizing maps, or called component maps. It's also a method for dimensionality reduction. This we won't touch. Good. This is one representation of such a manifold. So it's an easy one. It's like an S curve here in a 3-dimensional space. But if I look at that S here, I would say the data lies more or less on a 2-dimensional wrapped paper. So the dimensionality of this data space, it is actually 2-dimensional. And I have to define these 2 dimensions. So to represent this data, it will be best if I make an axis in this direction and a curved axis along this S. And I have the full data representation, but projected to 2 dimensions, even if these 2 dimensions are wrapped. Doesn't matter. And we will see that PCA is not able to unfold such a thing. because PCA is kind of a rotation, it's a projection. And you never can project that one so that parts of this S don't overlap. And for that we need nonlinear methods like MDS or TSME. And here are the different methods applied. Of course, PCA doesn't make any sense here, but we will look at local linear embedding, isomap, MDS, and TSME. So they all manage in some way to unwrap the S. So that actually from here to here, I more or less have a continuous decay of the values. Blue ones and the red ones, they're separated left to right, and I can make a classifier here, for example. So they're not mixed up here, they're nicely separated. And that's kind of a good way to do it. I have here a video from Google, I hope it works. And I just put it here because as a motivation, because I like the representation of the data they make. These visualizations are really professional.
Hi, I'm Ben.
Hi, I'm Martin.
Hi, I'm Fernanda. Machine learning is pretty complex, so we've been experimenting with ways to visualize what's happening. There's a core concept in machine learning called high-dimensional space. Here's one way to wrap your head around this concept. You can think about people as being high-dimensional. For example, take famous scientists. You can think about when they were born, where they were born, their fields of study. Each of these is like a dimension of that person. These dimensions become difficult to untangle when you think about different people, because someone might be similar in some ways, but very different in others.
But this is the kind of thing you can use machine learning for. With machine learning, the computer isn't told the meaning of these dimensions, it just sees them as numbers. And it sees each set of numbers as a data point. But by looking across all of these dimensions at once, it's able to place related points closer together in high-dimensional space.
Here's a concrete example where words are treated as high-dimensional data points. The important thing to remember is that we haven't told the computer the meaning of words. Instead, we've shown it millions of sentences as examples of how words get used. Here's a visualization of the results. We're looking at a subset of words that the computer has learned about. Each dot represents one word. Each word is a data point with 200 dimensions. Using a technique called t-SNE, the computer clusters words together that it considers related, and clusters form based on meaning, even though we've never taught it the meaning of words. Here is a cluster of numbers, months of the year, words related to space, people's names, cities, and so on.
We can also look closely at smaller sets of words. If we search piano, we can run t-SNE only on words related to piano. We get clusters of composers, genres, musical instruments, and more.
And this approach doesn't just work for words. For example, you can also treat an image as a high-dimensional data point. Here's a data set where lots of people wrote digits between 0 and 9. People write in all kinds of ways. So the question is, instead of us needing to manually code rules for all the ways people write, could a machine figure it out itself using machine learning? Each image is 784 pixels. The computer treats each pixel as a dimension. Again, using t-SNE, it clusters these images in a high-dimensional space. We've color-coded them so that it's easier for us to see what's going on. And you can see groups of digits clustering together. It's learned something about the meaning of these digits.
These visualization techniques we've been exploring can be useful for all kinds of things. That's why we're working on open sourcing all of this as part of TensorFlow, so that anyone can use these tools to explore their data.
Okay, that was the ad. No, it's really nice. Huh? It's nice what we can do without giving meaning to some features. Actually, we can cluster it, and that will be the topic also for the next week here. Clustering, unsupervised learning, how we can form groups out of unseen, unstructured data. Okay, we start with PCA, Principal Component Analysis. So the first question to you is, who has ever heard about eigenvalues, eigenvectors? Who is familiar with it, with this concept? So everybody, that's fine. Huh? Good, okay. So, because principally, actually, PCA is nothing else than a decomposition into eigenvectors, eigenvalues of the covariance matrix of the data. And we see why this happens. And what we try to do is actually we want to find a lower dimensional representation of our data by keeping the variance as big as possible. And it's the same to say this, or I can turn it the other way around. I want to have a representation of my data vector in a subspace, which is lower dimensional, as good as possible. So I want to find the best matching hyperplane in these lower dimension data, which best represents any data point. It seems two different things, but I will show that it's the same thing. Once you look at the biggest eigenvalues, once you look at the lowest ones, and it's just the same thing. It's like a medal from two sides. It leads to basic same thing. So the vectors, the eigenvectors that correspond to the largest eigenvalues, and we can select how many we want, represents actually this lower dimensional subspace we're looking for. Why is it that? And the number of these eigenvalues can be chosen. We can do it, and at the end, if we have n data points, we take n dimensions, of course, we could fully represent the data. Doesn't make sense, so it makes sense actually to choose the dimension of the lower dimensional space smaller than the data dimension. We call it a d-dimensional hyperplane. If you look at such a feature matrix, the data matrix, normally we have actually n samples. N can be quite big, thousands of data points, and we have p dimensions, p features, p different features. It would be in the case of an image here, it would be these 284 pixels of a single number in the n-nis data set. And here are the samples, number 1, 2, 3, and so on. If we calculate the covariance matrix, it's maybe x transpose times x here. That's actually the formula in case of a zero mean. Then we get a square matrix, yes?
Sorry, you say 284 dimensions.
Yes.
Where is that number?
The n-nis data set represents the pixels, or the pixels in the n-nis data set. Here, if I have a number like this, for example, the 6, something like that, the representation in the n-nis data set, it's just my example here, it's 28 times 28 pixels. And what we then do is actually we flatten that image to construct actually such a matrix, because we want to have it in a normed representation. It's this tidy data representation of data. And then if we have an array, this is a two-dimensional array, 20 times 20, 28 times 28. And if we flatten that, we get a vector, and the vector will be aligned like this. First row, also first, and then the second here, third. It will be a long, long vector. And this is then kind of the one-dimensional representation, or 284-dimensional representation. Because here on this axis, you always want to have data points in a high-dimensional vector space. So we have to flatten images. We have to make them flat. Same what you do actually also if you feed a neural network, you make the pictures flat. You feed them in parallel, all the pixels. Yeah?
So isn't the number of dimensions 784?
The dimensionality is 784, yes.
Oh.
Yeah?
I thought you said 284.
No, 700. Did I write? No? Okay. So this could be a number, and the 6 is then here represented by ones and zeros or gray lines. So if we calculate the covariance matrix, it will be a square matrix. And the nice thing is actually this x is a symmetric matrix, and it's real. So it's guaranteed that it has an inverse. And it's guaranteed that we can decompose it into eigenvectors, eigenvalues. That's the nice thing. And it's only p-dimensional. This could be 1000 dimensional, at least we have now reconstructed actually or reduced it to a matrix which is only 784 dimensional. Right? So, but this could be 10,000. And now the idea is to decompose it in such a way that we get a diagonal matrix out of it. In that we look for a subspace, and it's the space of the eigenvectors actually, where this matrix here, it's a symmetric real matrix, becomes diagonal. Which means actually we look for a rotation and a rescaling of our original data space such that actually the data can be represented in these components, in these main directions by a singular scalar value which scales along this direction. That's what we do. And in principle, in 2 dimensions, it's just a rotation along these principal components. And the new subspace will be, for example, Z1. If we take Z1 and Z2, we have 1, nothing. We have just rotated our original space, but we didn't reduce the dimensionality. But if we reduce it only to Z1, we've reduced the dimensionality by 1. Okay. Why does it lead here to an eigenvalue problem? We come to it, like here. So our goal is actually to diagonalize the covariance matrix XTX. And this U here, actually this is a matrix which is built out of the eigenvectors of this matrix XTX. So if we solve the eigenvalue problem, we can first get actually eigenvalues, and some can be 0, they're not important, and we will select the eigenvalues after sorting them. Means we put here the biggest eigenvalue, the second biggest, and in a descending row. And then we say, okay, we will select these eigenvalues such that we have just d dimensions. Then we have reduced it to d dimensions, and the rest we fill with zeros. So we make a projection to a lower dimensional space which has only d dimensions. When we together paired with such an eigenvalue is always an eigenvector. And these eigenvectors actually, they build first of all the transformation matrix U that transforms the X space into, let's say here, the Z space. So if I align the eigenvectors in a matrix, I get the transformation matrix U directly, which is used to transform from the X space here to the Z space, where, for example, the covariance matrix is diagonal. That's what I want to achieve. So an eigenvector, you know, is defined like this. A eigenvector V is something like lambda V. Means, okay, this is kind of like a stationary vector from this A. The A, the linear operation, linear function, it just means that actually if I have such a vector, it's only scaled by some value lambda. It's not rotated, stretched, or it's just stretched by a lambda. We find it, first of all, the eigenvalues by, for example, this one, that r minus lambda 1 equals 0. This gives us a polynomial which is n-dimensional. We solve for the lambda e. And then for the eigenvectors u, which are paired. And if I put these eigenvectors together, I get automatically actually the transformation matrix which I need. But the trick is now that I don't need all the eigenvectors. I don't need all the eigenvectors. I cut them and I prioritize them by the biggest. I take the d biggest eigenvectors, which I say, okay, they represent best the data. Why? We will just see. Okay. In scikit-learn, it's quite easy to transform it. We have it in decomposition, in the submodule decomposition. We make a fit transform, which transforms now the x vector, for example, here in this z vector, which I call here x2d, and I can reconstruct, using the inverse transform, the original space. But it won't be one-to-one identical. It can be that some vectors are flipped. because the order of the eigenvalues will be changed if I make the order. But in principle, it's the same space. Huh? And I get here, using the inverse transform, and not every decomposition method has an inverse transform, but PCA has, I can get it back from a low dimensional space and blow it up to the high dimensional space. And this can, for example, be used for filtering noise. This is a nice thing. Okay, how do we select these eigenvalues in this diagonal matrix D? In this rotated space, the eigenvalues, they correspond to the lambdas or to the variance of the x in that direction. And the variance is something that describes, okay, how much information in this is in that direction. The variance of the data, it's huge. There must be a correlation there. The variance is there. So normally what we do is actually we cut it and say we want to explain 80% of the variance of the data by this lower dimensional space. And according to this, if I said, okay, the number, the variance that I want to be able to describe in this data space is 80%, I can deduce then from this graph by just plotting actually the sum of the eigenvectors, cutting it by 0.8, the number of dimensions I need to represent actually 80% of the variance of the data. For example, in this MNIST data set, I would say we could reduce it here from 284 dimensions to 40 dimensions, which is quite drastic. Huh? And nice from this representation is actually that this representation is actually also shift invariant, a little bit rotation invariant. So numbers that are not totally centered, numbers that are not fully aligned, and so on, shifted a little bit, they will be represented by the same dimensions here. So it makes it more robust later for a classifier to recognize these numbers. So we get also invariant spikes. Okay, this is the total explained variance. Huh? And we can represent it by actually the sum of these eigenvalues. And we call it at some dimension here P, this is the full dimension. The full variance is just the sum of all eigenvalues. Because the eigenvalue is actually the stretching factor into this direction. If I have a multivariate Gaussian distribution, the variance would be here. For example, this one. Huh? But this is actually, this is lambda 1. And this one, the perpendicular one here, this would be lambda 2. And this we do in n dimensions. To explain the full variance, I have to explain this and this. If I'm happy with the variance only of lambda 1, I can just represent it along this line. In the many dimensions, I have to sum up the dimensions so that I can explain, for example, accumulated eigenvalues up to some desired variance. The variance is actually what I want to explain, this scattering, which is represented here by this eigenvalue. And how do we select this dimensionality? Either we define the variance that we want to have explained, 80%, 90%, then we can deduce the number of D, low dimensional, or we look at what happens if I go for more and more main components, and then we normally see at some point kind of an elbow curve, huh? Where there's a nick or an edge. And then we could stop because we can say, okay, additional dimensions, they only add marginal explanation for the variance. So I can stop there because the big win is here. Huh? So if we plot actually the explained variance, we get such a curve like before, and often they have some elbow edge here, where we can stop and say, this is kind of a good representation for the data. Let's select the dimensionality of the low dimensional space like this. Okay, in 3 dimensions, this would mean actually a projection to a hyperplane. And the hyperplane here is represented now by the eigenvectors, 2 biggest eigenvectors in this 3-dimensional space. The third one would explain this variance. The first one explains this variance, the second one this one. The third is perpendicular to each other. Probably you remember from eigenvalues, eigenvectors, that they build an orthonormal set actually in this space. So they span up the whole space. So each other is perpendicular to each other. Yeah? So it's an orthonormal space. Huh? And in this manifold, this is now a linear manifold, the data looks like this. And if we think, okay, we could classify, there's a good way to do it using a decision tree, using, for example, a support vector machine in this lower dimensional space, because the third dimension does not add a lot to the information of these data. But then the learner will have less difficulty, and it will profit from less overfitting. Because if we have very high dimensions, we have a lot of parameters, and we always risk that we have a problem with overfitting. So reducing the dimensionality of this vector space helps to avoid overfitting. Using now only a subpart of this transformation matrix U, we can project the original data to a lower dimensional space. And the reconstruction is just done using the transposed matrix, which is at the same time the inverse of the U. Because it's orthonormal transformation, then this is actually also the inverse here. And that's shown here actually. What we do actually is we fill the rest of the matrix just with zeros. This is a real zero, it's not an O or so. So we take only the k biggest eigenvectors into this U, and then we skip the older ones, the other ones, or also the informations of these after they have been sorted. And we can show that actually the reconstruction error in this subspace is minimal if I take p or d dimensions in that subspace. Let's assume we have a d-dimensional data vector, so it's one of the column vectors of our data matrix here. And we construct the full data matrix here, like this. Now the vectors are down like that. We have n samples here. And we want to project it onto an n-dimensional subspace with n really smaller than t. And I explain it now how we get actually to this eigenvalue problem. And we look at only one, the first eigenvector. Let's call this first eigenvector with the biggest eigenvalue U1. It's the first entry, it's the first entry of the transformation matrix U, and it's the first eigenvector which corresponds to the biggest eigenvalue. And we only look at this, what happens when we project it to that one. I define the data mean and the original covariance matrix now with a given mean. The mean is not 0 anymore. And now our goal is to minimize the variance in the subspace. The P stands for projected space, and it's a subspace, a lower dimensional subspace. What is the variance in that subspace? Not in the big dimensional space. So we project it using now only U1. We say, okay, let's do a one-dimensional projection. We take the x vector, transform it. It's like a scalar product here. We take the projection of x along U. And that's the representation of the first data vector here of the mean in this vector subspace, which is only spanned, it's one-dimensional, along U1, the biggest eigenvector. So the biggest eigenvector in our example now represents the full data space. And we want to project everything onto the biggest eigenvector, to a one-dimensional space. Then we calculate the variance in that subspace. So we have to calculate also in this subspace here, it's actually the transformed xn minus the transformed mean value squared. And if we do that, we get this one. U1t transposed covariance matrix C times U1. And this should be maximized. That's now the goal. We want to have the maximum variance explained in that one-dimensional subspace. So we want to maximize that. How do we do that? First, we can do that, but there's a second constraint. We want that the length of the U1 vector is 1. We normalize it to 1 so that we really have an orthonormal basis in that subspace. This is actually a second condition that we impose onto U. Normally, they're normalized, then we get the lambdas. So, what do we have? we define a Lagrange function. Has everybody heard of that one? To optimize Lagrange? Probably not. A Lagrange function with some conditions. It's normally the topic we want to optimize, maximize.
So yeah, if you have, also you can use the Lagrange or use it if you have optimization
Right.
problem that is not open or closed to infinity, but is only equal to
Right.
parameter. It's closed.
Right. If we have actually constrained optimization problems. Huh? So it's not infinity, but we have a condition which says the length of u1 here has to be 1. Huh? And every condition, every constraint we add using a new parameter, which is called a Lagrange parameter. Huh? So we want to actually optimize or maximize this one under the constraint that the length of the u1 vector is 1. And we can do it at the same time, simultaneously, defining a Lagrange function, which we then optimize. A function, a multi-dimensional function, is optimized by taking actually the gradient with all parameters here. So we take the derivative of this Lagrange function with respect to u1, which means actually this is the gradient with respect to u1. This is the partial derivative with respect to the Lagrange parameter 1. If we do that, if we derive here, if we actually get cu1 is lambda 1 u1. And that's the eigenvalue problem. Huh? So it comes from the fact that we want to maximize the variance in our subspace. This is represented by this one, u1 tc u1. We have a one-dimensional subspace. Now for this example, we're going to maximize the variance in that one, and we look for how does this u1 has to be? Huh? In which direction does it have to point? And what is the length of this one? Huh? What is the variance in that subspace? And we get it by solving the eigenvalue problem of the covariance matrix. Huh? So that's the reason why we actually do a decomposition into eigenvalues. It comes out of an optimization problem, which has the goal to explain most of the variance in this lower dimensional subspace. More or less okay? Good. Okay. The same thing, and I won't go here into detail for the interested ones. They can look at it. Now we look actually, the next step would be, let's take the second biggest eigenvector, the third biggest, and so on. Then we do not project into a one-dimensional, but a two- and three-dimensional subspace. The same thing applies here. What we have done now for one vector, we can also do for n eigenvectors, u1, 2, up, for example. Another way, and here I just cite Bishop here, so his book, Pattern Recognition, next. Actually, there's a nice explanation that actually the same thing is to look at the representation of the data. If you say, okay, we want to project this data into a lower dimensional space, how does this hyperplane have to be? In which direction does it need to be tilted so that I can represent actually the data as good as possible? And this means I have to minimize actually the error between actually the representation on my hyperplane on the actual data of the hyperplane. So I want to minimize this distance, this residual. And formulating this optimization problem leads to the same eigenvalue problem. So actually what we can say, if I look at the m biggest eigenvectors and keep them, then I would say I construct a projection matrix such that the variance in this subspace of the data is maximum. If I look at the d minus m smallest eigenvectors, I look at the errors here, which are here represented by these lines, by these stems, and I want to minimize this error. How do I have to put my hyperplane into this data bunch such that the quadratic length of these lines is minimized? And this leads to the same problem. So, meaning maximum variance of the data in my hyperplane is the same thing as minimizing the error or representing the data just by a projection onto this hyperplane. It's the same thing. Okay. Good. Okay. What you now can do is you can compress the data, let's say, to 40 dimensions from 784 to 40 and reconstruct the data and see how good your reconstruction will be. And what we observe here is actually that we get gray pictures back because it seems that actually the offset in the middle is gray. So if I take the mean of all pixels of all training data, it will be a gray. Right? And it predicts now a gray color as background, right? Because it doesn't seem to have a lot of information, a lot of variance. So it's considered by the PCA as being not important in terms of information. Whether the background is gray or white doesn't tell you whether it's a number or not. So it's not that an important dimension. So it pulls back actually gray images, and you see there are some artifacts here which come now from the lower dimensional representation, but the main thing is actually kept. And this is also a way that we can filter data if they're really noisy. We can just reconstruct these pictures if we have noisy picture by doing actually an inverse transform and get clean pictures again. And that's what we will do in the lab. Okay. Here, for example, we have chosen 95% of the variance. In scikit-learn, you can say n components equals 40, for example, then it will reconstruct a subspace which is 40 dimensional. Or you can also say n components is 0.9. Then it automatically checks, okay, then I have to select as many components that the explained variance is 0.9. Huh? So it's both